Hello and welcome to the 31st lecture of this short course called Behavioral Theory of Systems with a View Towards Data Driven Control. So, in the last few lectures we actually did obtain an answer to one of the fundamental questions of data driven control, namely, given a trajectory data, is it possible to identify the system's equations? Yeah. And what we saw was that the trick was to look at this data and then construct these infinite Hankel matrices W0, W1 first with only the trajectory, then with one shift, then with two shift, yeah, and you keep on doing this, and each time we notice that when we find out the left kernel of these Hankel matrices, they are identified, they are identifiable, or rather they are equal with the annihilating polynomial row vectors of degree at most equal to k. Yeah, and then we observe something fascinating about these left kernels, that at one point, after one point of time, you do not get any essentially new information at all. It turns out that each of these guys satisfy the fact that they contain their, so every annihilating polynomial, every the set of annihilating polynomials of degree at most equal to k will certainly contain annihilating polynomials of degree at most equal to k minus 1, but not just that, together with that it also contains xi multiplied to such polynomials, when the xi degree increases by the degree increases by 1 of each of those terms, that also is included, right. And it turns out that beyond the point this inequality, I mean this containment becomes an equality, yeah, and once that happens we do not get any essentially new annihilating polynomial. All of the higher degree annihilating polynomials are in fact obtainable as polynomial multiples of other lower degree annihilating polynomials. And now once that is achieved, we can stop at that particular saturation point and obtain kernel representation from that degree constraint annihilating polynomials, right. That is what the subject, that is what we discussed in the past few lectures. Now, as I mentioned in the last lecture also, that there is something little uncomfortable, something that makes you uncomfortable about this analysis, and that is with this data. I am assuming here that the data is this infinite time series. Now, often when we do some measurements to collect this data, we will not be able to get information as an infinite time series, but rather what would happen is we will get W0, W1, W2, yeah, up to certain time capital T, yeah, a finite time series data. It may so happen that we have such finite time series data for multiple trajectories, but in any case all of them are finite. Yeah. To make our life easier, we will assume only one trajectory, though, one trajectory information for a finite time is there. Now, the question is it really possible to do this identification, yeah, from the finite time series data as well? Well, one can easily check that one can still do that. One can obtain an MPUM for this D by once again looking at the Hankel matrices. H0 will be just W0, W1 up to WT. H1, now the sizes will change. H1 will look like W0, W1 W1, W2, W2, W3 dot 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 dot. This will go up to Wt because I do not have any more information than that, but this will go only up to Wt minus 1. That is how it will stop. So, this is what size? This is a matrix of size q number of rows with t plus 1 number of columns, whereas this guy has 2q number of rows, but only t number of columns. Okay. Likewise, you will get the other Hankel matrices as well. And I can ask this question that okay, I will still take I will still find out the left kernel of these guys, of these HKs, and from there I can also identify that if I am looking at all those annihilating polynomials of this finite time series data, and those annihilating polynomials also will form a submodule, and so essentially I can repeat what we have done with the infinite time series data. But that is not the question. The question is as follows. But suppose that there was this underlying behavior, right? This is the ground truth, the underlying behavior that generated this data, that generated this W, and I want to identify this B. So, my goal is not to just find an MPUM that explains the data, but rather to find out this B that I am guessing has generated this behavior, this generated this data. I want to identify this B. Can I do that from this finite time series data? You see, it is a different question than MPUM. I have a ground truth B, I do not have the full data about this B, I have data about one trajectory, that also a finite time series data, and in that scenario is it possible for me to identify this B? It turns out that under certain conditions you can do that. So, under certain conditions one can just mimic the process that we did for the infinite time series data, to get to be able to identify this B itself. Okay. Of course, what conditions? The conditions should be imposed upon this time series, this finite time series data, and what is that? That is what we are going to investigate now. But before we do this investigation, we need to derive certain properties about these behaviors. Suppose there is a behavior given by the kernel of a polynomial matrix like this, right, without now bothering about this question of whether this identification is possible or not, whether I have a finite time series data, infinite time series data, what do I do with the time series data. We are putting all those questions on hold for the time being, but rather what we are going to do is we are going to derive certain properties about these behaviors. Okay. Some properties that we have not discussed so far about behaviors, some properties will derive, and with those properties we will see that we will derive the condition under which it is possible to actually do the identification with a finite time series. In order to do that, we first need to define these objects which are called restricted behaviors. I first define B0. What is B0? B0 by definition is the collection of all how to denote this. Let me use this letter V. All vector V of size q such that V is equal to W0 for some W in B. So, I look at q sized vectors which are in fact initial values of all the trajectories in the behavior, right. Likewise, I define B1 as the collection of all vectors V in now size 2q such that V is equal to W0 W1 for some W in B. You see the first two values of a trajectory. So, I look at all possible trajectories and from there I fish out all their initial two values, the first two instants, 0th and the first instance. Look at those vectors, club them together one after the other, and I take them, I collect them, and that gives me my B1. I am sure you can understand what will be the definition of a particular BL. BL is a vector V in R L plus 1 times Q, such that V is equal to W0 W1 dot 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 up to WL for a W in the behavior B. That is my BL. Okay. Now, notice that each of these guys are finite collection of finite sized vectors. So, of course, they are subspaces, they are subsets to start with. This is a subset of R q, this is a subset of R 2 q, this is a subset of R L plus 1 times q. Okay. These are subspaces also. Why? Because this behavior, the behavior that we have started with, this B, is actually a linear vector space, is a linear vector space, because it is the kernel of a polynomial matrix. No, it is a linear vector space. Now, it is closed under addition and multiplication. You can easily check that if V1 is there in, okay, if V1 is there in BL and V2 also is there in BL, that means for V1 there is a trajectory W1. So, V1 V1 must be equal to W10 dot 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 up to W1L, where W1 is a trajectory in B, and V2 must be equal to W02 dot 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 up to this, where W2 is in B. Correct. So, obviously, V1 plus V2 can then be written as W1 plus W2. That is a legitimate trajectory in B, because B is a vector space itself. That is it. Correct. That is also there in BL in that case. So, therefore, all of these guys are vector space, vector spaces. So, they are in fact subspaces of these guys. Because they are subspaces, I can talk about their dimensions. And like before, with a slight abuse of notation, I am going to define dk to be equal to the dimension of this restricted behavior k. Okay. Just like before, the way we did with the Hankel matrices. Before I come to the okay, but that is fine. That is okay. Just like we did with the Hankel matrices, you can easily check that D0 is less than or equal to D1 is less than or equal to D2, and so on. The dimension of these vectors of these restricted behaviors will keep on increasing, or it will at least remain the same. Yeah, it will certainly not be, it will certainly not decrease. But like before, I can define rho k to be equal to dk minus 1 with rho 0 defined as d0, and in that case what will happen is rho 0 will be bigger than or equal to rho 1, will be bigger than or equal to rho 2, will be bigger than or equal to rho 3, and so on. This goes to you as an exercise. Just verify that this is true, and you can take help from what we have done in our past lectures, and you will just notice that it is essentially the same argument with which we proved that these row numbers will keep on decreasing for a Hankel matrix. Yeah, the same argument will go through, will also take you through this through this case, when instead of Hankel matrices rank, we are defining it as dimension of BK, dimension of the restricted behaviors. Same logic will apply, and we will get that these numbers are non-increasing. Because these numbers are non-increasing, they will saturate, and because they will saturate, I can make this statement that okay, limit k tending to infinity, rho k will be there, and that will be your rho infinity. Yeah, once rho infinity is there, okay, we will also do the following. N is the annihilating module of the behavior, okay, and the same definition for these guys apply, and we will notice that this Nk is identifiable with Bk perp, right. Every annihilating polynomial of a polynomial whose degree is at most equal to k, they are in fact in the orthogonal complement of these restricted behaviors. Look at their definitions again, yeah, look at their orthogonal complements. They are in fact identifiable with annihilating polynomials. Okay. Now, if that is the case, then like before, it so happens here that B k plus 1 perp always contains B k perp plus xi times B k perp, like before, yeah, because of this shift invariance business. But beyond the saturation point, we will have B k plus 1 perp will be equal to B k perp plus xi times B k perp. So, we do not get any more new equations, yeah, essentially no new equations are there. Every equation is in fact obtained by polynomial as polynomial multiples of old equations. Okay. Now, once we have that, once that saturation property is there, like before, to identify B, if I had information about these restricted behaviors, it would be enough to find out B k perp. If we can find out B k perp, we are done, right. I am doing this purposefully a little quickly, because you see this is something that we have already done before with Hankel matrices when we have infinite time series data. But now here if instead of one trajectory data, if we have all the trajectory data, yeah, data for all possible trajectories, which is in fact the collection of which is these B restricted behaviors Bk. If we have information about that, then we can identify the system itself, the system B itself. Okay. Now, so the point is as follows. So, here we come at the crucial juncture, the crucial point. Notice now that if I have B capital K, or rather let us say this situation I have, say L is bigger than or equal to capital K, and I have this BL. If I know this BL, then finding out BL perp should be enough, because L is beyond the saturation point, and BL perp, the data that I have about BL perp, will give me this matrix R sigma such that kernel of R sigma will be equal to B. Yeah, kernel of R sigma will give us everything in this BL perp, but everything in this BL perp also means that we have information about all of B perp, in fact all of annihilating polynomials. Fine. What is the data that I have? The data written in the form of a L size Hankel matrix looks like this. It is a single trajectory data, right, W0, W1, W2 dot 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 WL, W1, W2, W3 dot 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 WL plus 1 dot 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 dot. This certainly will be WT, but that means this will be W, T minus L, right. This will be W T minus L plus 1, W T minus L plus 2 dot 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 like this. So, this is H L. Okay. Notice the following. What is the column span, of course, over R of this Hankel matrix H L? Each column of this matrix is the restriction of a trajectory up to L, isn't it? This is W restricted to L. This is one shift version of W, that is sigma W restricted to L. This is sigma square restricted to L. So, this is W restricted to 0 to L. This is sigma W restricted to 0 to L, yeah, and so on. This is sigma square W restricted to 0 to L, like this. So, then I actually have how many T minus L plus 1 such restrictions of we have 0 to L restrictions of T minus L plus 1 such trajectories. So, I have a few trajectories from the behavior, and whose linear combinations I am looking at. They are restricted versions from 0 to L, and I am their linear combinations I am looking at, which means that this must of course be a subspace of BL, isn't it? Okay. And my goal was to find out BL pub, right. Now, notice, if column span of HL is contained in BL, then that immediately means left kernel of HL will contain BL pub. So, that means I will have equations, right, but I do not have exact information about BL pub. I have something which is bigger than BL pub, right. So, I have informations about a smaller behavior, because I am having a bigger module. So, I have a so I do not identify B per se, but I identify a behavior which is smaller than that, which explains the finite time series data. But my goal was to obtain actual behavior. When will that happen? Obviously, if instead I have these two equal, right, in that case this will also be equal, and I am done. Left kernel of HL will allow me to identify the entire behavior B. From the finite time series data, I will still be able to identify the whole system. But here is the question, that when is this true? When is column span of HL equal to BL? That is the question. Okay. And it turns out that this is, there is a sufficient condition for that is this famous lemma, which is called the persistency of excitation. When the trajectory data that I have, the finite time series trajectory data that I have, if the trajectory data has been generated through an input which is persistently exciting, then it is guaranteed that this Hankel matrix that you get, the column span of the Hankel matrix, is in fact equal to the behavior. Yeah. But what is the meaning of persistently exciting, persistency of excitation? Yeah. Why should it mean that this for under persistency of excitation this will be true? All these questions will still have to answer, right. But in order for us to answer that, we will need to look at these invariants a little more closely, yeah, especially this one, the dimension of these restricted behaviors. We will have to look at these guys a little more carefully, and that is what we are going to do now, and we will continue doing this in the next few lectures. So, first we want to understand this invariant D, dk. Yeah. is the dimension of B restricted to K. Okay. Now, when we look at this B restricted to K, see, we although we did not discuss this, but this is also true. We did not discuss this even when we are discussing behaviors, but given any kernel representation behavior, it is possible to write them down as a input state output representation under proper input output partitioning. When you have a proper input output partitioning, you have a transfer function which is a proper transfer function, and once you have proper transfer function matrix, you know all the tricks that are there in your multivariable control courses, which allow you to derive a state space representation, and you may assume that the state space representation will be observable. You can also assume that the state space is controllable provided the behavior is controllable. So, we are going to assume that our behavior B to start with is controllable. You know, there is some underlying R sigma, right, which generates this B as its kernel. So, this R sigma is such that this R sigma R xi is factor left prime, we assume that. This is factor left prime, so controllable. So, we will also, so a controllable behavior which is given by a state space representation which is minimal. So, it is controllable and observable, x k plus b u k and y k is equal to c x k plus d u k. Okay. Minimal, which means controllable and observable. Okay. Now, from here it follows that if I want to write down u0 y0, that is w0, u1 y1, that is w1, u2 y2, that is w2. Let me write this down up to this, and then we will see what happens in general. What is this? u0 is what? Let me just put some blank matrix here, and then on the right I will write whatever is independent, whatever choice I have. x0 I can choose freely, so I write x0 here. The input u0 is chosen freely, u1 is also chosen freely, and u2. So, that is the free vector that is of our choice, free vector. And then there will be this matrix, correct. Because this is a free vector, the dimension of the space of all possible such w0, w1, w2, that means dimension of B2 will then be given by the rank of this matrix, right. Because this is a free vector, this, when this acts on this, I get B2 essentially is the image of this matrix. Because B2 is the image of this matrix, the dimension of this subspace B2 must be the dimension of the image of this matrix. Dimension of the image of the matrix is the column rank, and column rank is equal to row rank, which is the rank of this matrix. So, it is essential for us to find out the rank of this matrix. Now, what is this matrix? This is, say, this multiplies to x0, this column multiplies to u0, this column multiplies to u1, this column multiplies to u2. What is u0? This is just identity 0 0, that is it. What is y0? y0 is c times x0 plus d times u0, right. So, c times x0, d times u0, that is it. What is u1? u1 is 0 0 identity 0, and then y1 is equal to c times x1 plus d times u1, but x1 is equal to c times a x0 plus c times x1 is a plus b u0, right, plus d times u1. That is what we have. Okay. So, that means this is going to be C A, C B and D and 0. That is my u1. What is u2? 0 0 0 identity, And what is y 2? Y 2 of course, let me just write it down. This is going to be c a squared x 0, then c a b u 0, then c b u 1, and then d times u 2. So, that is it, that is the matrix. So, in order to get the dimension of B 2, all I need to do is I need to find out the rank of this matrix. Okay. So, in general also, if you go up to k, up to the kth w k, the same pattern of the matrix will be repeated, and all I need to do is I need to find out the rank of this matrix, and that will give me the dimension. What is that rank, and why should it reveal that? That means the dimensions keep increasing, but then if you look at the difference of the dimensions, the consecutive differences in these dimensions, it will turn out to be a non-increasing sequence. Yeah, that will be revealed once we have a closer look at the rank of this matrix. This and many more is what we are going to do, what we are going to look at in the next few lectures. Till then, take care of yourselves. Bye.